Hi, Module 3. This is Part 4, and we're going to start talking about topography elevation-based small microclimate or weather conditions on location. And once again, I'm going to flick over to a different slide set of images because the slides provided by the text is lacking in these images, and it just makes it easier to understand. All right, so now let's talk about weather conditions within a mountain or a high elevation regime. And while we don't have a lot of high mountains here on this coast, it is something to make note of because we do have some in the upstate New York. You can consider the Catskills having this natural climate variation, and you can also look at Vermont, New Hampshire, so we can go up the line and see a lot more of this. Or if we go inland a little bit, on the East Coast, we can get to some of these mountains. And so mountain and valley breezes. Once again, they're named for where the air is coming from. So during the day, the sunlight will shine down and it will hit the mountain. And the parts of the mountain that it will actually shine on first is the topmost parts of the mountain, right? So the top of the mountain starts to get its little warm up, where the valley was sheltered from the sunlight for a while and takes quite a while for the sunlight to come up over the mountains to actually shine down in here, which means that the air molecules over the top parts of the mountains were able to warm up before the ones in the valley were even exposed to sunlight and got heated. That creates a natural set of low pressure over the top of the mountain and high pressure over the bottom of the mountain. Now, anybody who enjoys a good winter sport has been up to the top of the mountain and has felt how at the top of the mountain, the wind rushing up the mountain makes it feel like you can blow right up and over the mountain, right? So you've felt that natural pressure movement. This is because the colder air down in the valley creates a natural high pressure down in this location, where this is a natural low pressure, and that low pressure air is rising up into the atmosphere, right? So I have the natural rising. And this one, on the other hand, is making a wind condition because they're under so much pressure where they're pushing up the mountain to fill the space that was once occupied by the molecules at the top of the mountain. This causes a breeze known as a valley breeze. The bottom of my mountain is the valley, right? And the breeze is named for where it's coming from. So this is my natural valley breeze. And this is what occurs on a mountain during the day. On the other hand, at night, if you were to step out while you are out in your winter sporting and you're going to go out for the evening, on the other hand, and you were like, oh, well, I don't need to bundle up that much. It wasn't that cold at the bottom of the mountain, right? At night, the opposite occurs, and all of a sudden it's really windy at the bottom of the mountain, and it's very cold at night at the bottom of the mountain. And that's because the top of the mountain did all the sharing of its heat energy all day. It was getting heat up with the sunlight first, and it had to share it all, where the heat energy at the bottom of the mountain didn't need to share. It was absorbing. It took a while to warm up, but it got to maintain that heat and allowed for a natural low pressure to begin to occur in the center part of the mountain, so right down in the valley, right? So this is where the low pressure is. On the other hand, these air molecules have shared energy all day. Now they're slowed down. They're cooled off. They are under very high pressure. So while these molecules are warm and are less dense and therefore rising, these air molecules are cooler and they are more dense and they are under high pressure. And so they rush from their high pressure location to the place with space, the low pressure location, creating a natural breeze known as the mountain breeze. And this is what occurs in mountain locations at night. So once again, this is another micro weather condition. This is your valley and mountain breeze systems. I'm going to flick over yet once again to your major PowerPoint, and then I'm going to actually flick to another set of images because once again, it's just easier to explain these with images. All right, the next small microclimate is what's known as daytime warming and nighttime cooling. So on a normal day, when there's no clouds in the sky to interrupt sunlight entering the atmosphere, we can see sunlight naturally dropping down through the atmosphere layers and reaching the Earth's surface and being absorbed by the Earth's surface, and then the Earth radiates it back up as thermal infrareds, making it warm. And I'll see a natural warming process. On a day without a lot of clouds, I will have the warmer point of my day being mid-afternoon, right? So it will steadily increase in temperature. On the other hand, when I take the sunlight away, because I've moved out of the circle of illumination and nighttime has set in, I have nothing actually warming up the Earth's surface, and therefore all of that warm energy that the Earth's surface had is moving and sharing itself with the atmosphere. And those two are trying to meet equilibrium, and it's cooling off the Earth's surface. And I will find the coldest point of my evening being the moments right before sunrise. Those moments right before the sun comes up will be the coldest point of my night. And this is natural nighttime cooling. Now, everything gets a bit wonky when I throw some clouds into the mix, because on a day that's good and cloudy, the sunlight cannot reach the Earth's surface. And so with all those clouds up in the atmosphere, I will see that day maybe get progressively colder, if not stay the same throughout the day. And so I will see what's called daytime cooling. So when I have full cloud cover and sunlight cannot reach the Earth's surface to allow it to absorb that heat energy and radiate it out as thermal infrareds, I will see a natural cooling off of the atmosphere down here in the troposphere. Now, on the other hand, if I get a lot of cloud cover at night, all of that heat energy that the Earth's surface has absorbed will begin to share with the atmosphere, and it will send it up and out into this top part of the atmosphere, but it will reach the cloud cover. And those clouds will take that heat energy and absorb it themselves, because they are a greenhouse gas. They're made out of water. Water is a greenhouse gas. Greenhouse gases like to absorb thermal infrareds. And so they'll absorb those thermal infrareds and they will radiate out more thermal infrareds. And so they bounce those thermal infrareds back, and it creates this little thermal blanketing that occurs. And this means that the night tends to get hotter. And we all know what I'm talking about. We've all experienced those summer nights, which are really cloudy, and the sky almost looks pink because of all the light pollution actually bouncing off the clouds, that are just sticky and hot. And these have to do with these nighttime warming events where it's cloud cover and there's nowhere for the heat energy to escape to in the upper parts of the atmosphere. They're just getting bounced off the clouds and absorbed and radiated back down towards us. And so this is another microclimate. So once again, we're going through microclimates. Now, leaving the concept of microclimates, I'm going to jump to images of the heat index and cold index, because you're going to need to be able to utilize these to determine what temperatures our bodies are reacting to versus what temperatures we are actually measuring.